The proposed end-to-end approach for reconstructing the electrostatic potential volume of a sample directly from 4D STEM datasets combines phase contrast imaging with atomic resolution electron tomography. This method overcomes limitations of traditional imaging methods by utilizing multi-slice ptychography to compensate for the missing wedge effect and recover several slices at each tomography tilt angle. The algorithm is initially tested in simulation and experimentally demonstrated, recovering a Te nanoparticle with Sub-Ångstrom resolution. The reconstruction workflow consists of 3 steps: fast reconstruction using bright field data, estimation of global tomographic alignment parameters, and final reconstruction of the sample's 3D volume. This innovative method offers a significant improvement in imaging capabilities, particularly for thicker samples and light elements, with potential applications in materials science and structural biology. The end-to-end reconstruction workflow for 4D STEM data begins with the bright field reconstruction and aberration calibration. The weak phase images are reconstructed using the SSB method on uncalibrated datasets, and the optimal defocus for the bright field reconstruction is used for probe initialization. The multi-slice ptychography reconstruction then produces several slice images for each tilt angle, which are summed into 2D phase projections for joint reconstruction and alignment. To model partial coherence, a set of partially coherent modes is introduced, and the measured intensity becomes the incoherent sum of these modes. The multi-slice Tycho (MSP) algorithm is used for joint object, mixed-state probe, and position retrieval using multi-slice ptychography. This algorithm iterates through steps that include initializing aberration surface, calculating mean intensity, and setting up the initial probe and position refinement parameters. The algorithm then iterates through a loop that updates the volume, probe, and position parameters, outputting the final reconstructed volume, position, and probe. In the context of joint rigid alignment and linear tomography, the electrostatic potential of the sample is reconstructed, and a 2D projection of the sample can be formed by summing up the real part of all reconstructed slices. Using the potential projection for each angle, the affine transformation can be calculated using tomography, with the workflow shown in Figure 1b. The algorithm starts with loading the 2D projections and specifying the tilt angles. The 2D projections are preprocessed by applying an intensity threshold and downsampling the images. These preprocessed images are considered as the sinogram target of the loss function. The affine alignment includes 3D rotation angles and 2D spatial translation. The rotation matrix R is defined following the tomography convention in the popular cryo-EM processing package RelyOn. The iterative tomography alignment process consists of 2 nested loops. The outer loop updates the alignment parameters, which are then kept fixed in the inner loop. The inner loop performs the tomography reconstruction using an adjoint radon transform R on a 3D model of the particle, with the 2D projection images and the alignment parameters from the outer loop. A new set of projection images at the same tilt angles of the 3D model of the particle is considered as the sinogram model. The research paper presents a novel method for end-to-end ptychographic tomography, integrating the reconstruction of the electrostatic potential volume, alignment parameters, and multimodal probes in a single computational framework. The approach utilizes a forward model based on the sinogram model and sinogram target, with a mean squared error loss function calculated using the amplitude of the modeled diffraction patterns and the measured 4D STEM data. The algorithm starts with initializing the volume, alignment parameters, and multimodal probes, iterating through each tilt angle until convergence. The simulation benchmark demonstrates the algorithm's performance on a cube-shaped PT at aluminium oxide core shell nanoparticle, showing acceptable alignment differences and high accuracy in the reconstructed volume compared to the ground truth. The paper also discusses the development of a novel end-to-end reconstruction algorithm for ptychographic tomography, focusing on the experimental demonstration and resolution analysis. The experiment involves collecting a 4D STEM dataset at various tilt angles, achieving a resolution of 3.28A with a total fluence reduction of 12 times compared to previous methods. The authors present a novel joint reconstruction algorithm for multi-slice ptychographic tomography, addressing the missing wedge effect in electron tomography. This algorithm expands 2D projections to 3D volumes at each tilt angle, recovering information in the missing wedge direction. Demonstrations under low-dose conditions achieve near-isotropic 3D resolution with a tilt range of plus or minus 45 degrees in simulation and plus or minus 53 degrees in experiment. The algorithm's potential is shown in imaging both high and low atoms with a tilt range of 90 degrees. Experimental results involve a Te nanoparticle and a carbon nanotube using the TEAM 0.5 microscope. The paper also discusses advanced techniques in electron microscopy, including phase retrieval methods, the importance of minimizing the missing wedge, and the benefits of dual-axis tomography. A new method for reducing the missing wedge using dual-axis tomography is presented. The authors emphasize the need for precise control over microscope parameters and detector settings for high-quality images. The experimental setup for end-to-end ptychographic tomography detailed in Table 2 involves a microscope voltage of 80 keV with an SFEG electron gun, featuring a source size of 0.8 A. The CC value is 0.6 mm, with a defocus spread of 6 nanometers and a convergence semiangle of 25 mrad, providing a depth of field of 9 nanometers. A 4D camera operating at 87 kHz was used as the detector, with a pixel size of 4.14 × 10⁻³ A⁻1, binned to 0.0272 A⁻1. The detector outer angle was 50 mrad, and the reconstruction pixel size was 0.397 A. No energy filter was employed, and the experiment involved 36 projections, using 26 for analysis. The tilt range spanned from 53.9 to 52 degrees. A total of 34,560,000 diffraction patterns were recorded, with 8,423,259 selected for further processing. The stem step size was 0.397 A, and the dwell time was 11.49 microseconds. The probe current measured on the flue screen was 40 picoamperes, resulting in an electron fluence accumulated in the experiment of 6.28 × 10⁵ A². For the reconstruction, an electron fluence of 4.4 × 10⁵ A² was utilized, with each projection receiving an electron fluence of 1.72 × 10⁴ A².